So we'll begin chapter 2 by looking at atoms, isotopes, and bonds as the first part of our unit. Since physiological processes are based on chemical reactions, we have to have a general understanding of the chemical principles, okay? And so hopefully this is a big review for most of you. So let's begin with atoms, and these are the smallest unit of an element. So an atom has a nucleus, which has positively charged protons and neutrons. So in this example, so here we have hydrogen, and so here we have our nucleus, and so this example only has one proton. In our example here of carbon, carbon now has 6 protons and 6 neutrons, and together that again makes up our nucleus. So protons are going to be positive, so P for plus, and then neutrons are going to be neutral or no charge. Okay? So around the nucleus, what we have are different orbitals. And so within the orbitals, we'll have electrons. And so electrons will be much smaller in size. And so they go around the nucleus. And they have a negative charge. So electrons here have a negative charge. So in our example of hydrogen, here we have one electron. And so that will be negative. And so in the positive proton for the nucleus. In our example of carbon, what we have are 2 electrons that are going to be surrounding the nucleus in the first shell, and then the second shell has 4 more electrons. So the atomic mass is going to be equal to the number of protons plus the number of neutrons. So take a moment, what is the atomic mass of our example for hydrogen? So 1, very good. And then what is the atomic mass for carbon here? So this would be 12, right. And so the atomic number is going to equal just the number of protons. So for hydrogen, the atomic number is going to be 1. And then so for carbon, atomic number will be 6. So the electron orbitals, we had just a little bit of an introduction in the last slide, are going to be the shells that surround the nucleus of the atom. So for instance, if I draw a little example here, so here we have one, pretend like that's my nucleus, and then here we have this first shell for hydrogen, and so it only has 1 electron, okay? And so those electrons are going to be circulating around, all right? So the electrons are going to fill these shells depending on how many electrons they have for each element. And so starting with the closest one, the first shell always holds a maximum of 2 electrons. Every shell after is going to hold a maximum of 8, okay? So let's do a different example in another color. So here, say we have our nucleus that I'm drawing here. So this first shell around the nucleus can only hold 2 electrons, but then every orbital after that can hold a maximum of 8. So if it has 3 shells, for instance, it would just continue having 8 electrons, and up to 8. That's the big key feature, okay? It can't hold any more than 8 afterwards. All right, so atoms are going to be the most stable when they have their last outer shell that's filled. Electrons in an unfilled shell participate in a lot of bonding, and so these are called our valence electrons. So let's look at a number of isotopes, which are very important for physiological processes, and especially when we look at a research setting and clinical research. So isotopes are going to be atoms of the same element but with different number of neutrons, okay? So let's look at this example here where we have iodine 131 versus iodine 127. So what we have here is that the atomic number is the same but the mass is different. So the number of protons stays the same among isotopes. The thing that changes is the number of neutrons, okay? So iodine 127, so this is our normal iodine, and then so our isotope then would be this one where we have 78 neutrons instead of 74, okay? And so some isotopes then are radioactive, and so in this example, the iodine 131, this is used for treatment in thyroid cancer. And so it has a short half-life, and so radiation for cancer treatment diminishes quickly without killing or harming other tissues. And the cool thing is it has a very high success rate, one of the highest for cancers at about 95%. Another example is iridium 192, another isotope. And so these implants are used within the head and breast, and so usually they're introduced by catheter to help with cancers within those regions. And then lastly, iodine 125 and palladium 103, also examples of isotopes used to help with early stages of prostate cancer and have all been very effective at that. These elements are going to be some of the most common atoms that we'll see over and over again in physiology, so it'll be very beneficial to understand and have a good grasp of what they mean. So here we have what the atom is, what their symbol is, and so I would be familiar with what their symbols are. Take a moment and think now, what does the atomic number mean? What does the atomic mass mean? And then what are the differences in the electrons in their shell? So, just so we have a clear understanding, atomic number, this has to do with number of positive protons, right? And only protons here. Atomic mass is going to be the number of protons plus the number of neutrons, okay? And so where do we find both protons and neutrons? In the nucleus, exactly. All right, so then when we look at electrons within our shells, remember that the maximum number within shell number 1, which again is closest to the nucleus, is only 2, whereas every shell elsewhere and outside is going to have a maximum of 8. Okay? Atoms are also responsible and capable of having different types of chemical bonds, and we have different classification of bonds. So in general, let's begin with what is a chemical bond. And so these are formed when electrons and atoms interact. And so the number of bonds an atom can form is determined by the number of valence electrons. And so valence electrons then are shared because energy levels will overlap, okay? And so, for example, hydrogen has only 1 electron. It needs 1 more to fill its inner shell, so that way it means it can form a bond because it wants to have a complete shell because it's a stable, happy molecule then. In our other example of carbon, carbon has 6 electrons. 2 electrons fill the inner shell, and then 4 valence electrons fill the outer shell. That means that it needs 4 more electrons so it can have up to 4 bonds to complete that set of 8 within that shell. The way that electrons then share has a different type of bond, okay? So the first one is a nonpolar covalent bond, where this is shared equally among electrons. So example of this is 2 chlorine atoms. To put it in a different perspective, this is when 2 kids are playing and sharing together, okay? The other type that we have is a polar covalent bond. So this is where there's unequal sharing between 2 atoms. So that also means that there's going to be one that has a more positive end between the 2 atoms and then one that will have a more negative end. So oxygen and hydrogen is a great example within water where oxygen tends to be the more negative and then hydrogen tends to be the more positive end. So an example of this in other terms is when one kid bullies another and plays with more toys, okay? So oxygen is going to be the bully and is going to play with more of the toys or electrons than hydrogen would. So between the nonpolar and the polar bond, which of the two do you think is going to be a stronger bond? So it will be the nonpolar covalent bond because it takes a lot of energy to break that equal sharing. And so physiologically, this is important because peptide bonds for proteins are what help to make those chains of amino acids, and so those are very hard to break. Whereas polar bonds, such as with oxygen and hydrogen and water, these are weaker and are easier to break. So if we look at water, let's remind ourselves that water is a polar molecule, meaning that there's unequal sharing of those valence electrons. However, though, water is going to be a great solvent because substances are able to dissolve in it. And it can form a strong hydrogen bond where polar molecules, which are covalent bonds, or form covalent bonds, may dissolve in water and are called hydrophilic, okay, water-loving. So examples of hydrophilic substances include salt, sugars, and amino acids. Nonpolar molecules, which again have equal sharing of their valence electrons, do not dissolve in water and are called hydrophobic, so water-fearing. Okay, so examples of these will be oils, fats, and alkanes, which are saturated hydrocarbons like methane and propane. Another type of bond are ionic bonds, and so ionic bonds are where there's one atom that gives electrons to another so that both have filled valence shells. All right, so this creates one that is a cation, which is the electron donor becomes positively charged, okay, so cation for positive. And then the second one becomes an anion, where the electron receiver, so you're receiving a negative charge, becomes negative. So an anion is for negative. So cations and anions attract each other with their positive and negative to form ionic compounds. Okay, so here's an example. We have sodium and here we have chlorine. All right, so sodium is going to be a cation where it's going to donate its electron. And so here, represented in this red electron, it will donate its electron to chloride or to make a chloride ion. Okay, so now chloride is negative because it's gained an electron. So the negative side, another example of this would be with water. The negative side of water will be attracted then to the cation, and the positive side of water will be attracted then to the negative. So this is a strong attraction that pulls the ions apart, and so water molecules then surround the ions to form hydration spheres, where these free ions are critical in many physiological processes. So individual ionic bonds then tend to be weaker than covalent bonds, where in most ionic compounds will easily dissociate into water. And so the last type of bond that we'll cover are hydrogen bonds, where this is a little bit unique because this is not based on electron sharing, okay? So these are weak bonds that are formed between two polar molecules based on opposite charges attracting forms between a positive and a negative, okay? And so an example of this would be between water molecules, where these hydrogen bonds here from several other molecules of water are going to bind to one another, okay? And so This type of hydrogen bonding then is responsible for the surface tension that we see, as well as capillarity. This is formed between amino acids on proteins, and this helps to produce 3D structures within a protein. Also, we find this holding together DNA molecules, the two strands together. So while they may be weak, they are very important in terms of physiological processes.